Hi folks, today we're starting in on Module 6, which is all about matter and energy. So first we're going to talk about matter. The kinetic molecular theory is a way of talking about the different states of matter, solid, liquid, gas, and describing the characteristics of those different states of matter by talking about their particles. In order to talk about these states of matter, we need to talk about the particles first. So particles of matter are always in motion. They are constantly in motion. The kinetic energy, the speed of those particles, increases as temperature increases. At 0 Kelvin, that's absolute zero, and all motion stops there. So particles are constantly in motion unless they are at 0 Kelvin. And scientists have not been able to recreate 0 Kelvin. They've gotten close, but not all the way to 0 Kelvin yet. So temperature is in fact a measure of the kinetic energy of particles in a substance. So let's look at how the different states of matter are different to each other. Solids have a very low kinetic energy. The particles vibrate, but they can't move around. Because of that, they have a fixed shape, they have a fixed volume, fixed volume, and that makes sense because the particles aren't free to move around, so they can't just move wherever they want. They're kind of locked in place next to each other. Notice when we represent these particles here locked together in a glass, they are still moving. So sometimes people draw these kind of like quotation marks, like you might see in a cartoon to show that something's kind of vibrating in place. But these particles are vibrating in place. They're not moving around. Liquids, on the other hand, the particles have a low kinetic energy, not as low as in solids. The particles can move around, but they are still close together. And because of this behavior, liquids do have a variable shape. They take the shape of their container, but they still have a fixed volume. So these particles are moving a little bit more around here, faster than what we saw in the solid state of matter. The third state of matter that you need to know about are gases, and gases have the highest, particles and gases have the highest kinetic energy out of all of the states of matter. The particles can separate from each other and can move throughout the container. And because of this behavior of the particles do have, gases have a variable shape. They take the shape of whatever container they're in, just like a liquid does. They also have a variable volume. Gases will expand to fit any container that they are in. So if you have compressed gas in a tank, like maybe a helium tank for blowing up balloons, and you open up the valve to the tank or punch a hole in it, which would be extremely dangerous, but if you let that gas out, it doesn't stay compressed in that small volume. It expands to fill whatever room you're in. So when we talk about moving between these different phases, solid, liquid, and gas, it helps to look at a phase diagram for a substance. A phase diagram has temperature on the x-axis and pressure on the y-axis. And as you move up in temperature or up in pressure, the phase, whether you have a solid, a liquid, or a gas, can change. You can see that at cold temperatures, think about water here, at cold temperatures, you're more likely to have a solid. So the solid, not surprisingly, exists here at low temperatures. It also exists at high pressures. Okay, low temperatures and high pressures is where you have solids. When your temperature increases, then, using water as an example, your ice cube will melt into a liquid, and then you have liquid material. And then thinking about your ice cube again, if you heat it up even more, eventually you would get to the point where you would boil the liquid and turn the liquid into a vapor, turn it into a gas, okay? And then that is at these higher temperatures here. Notice that if you get to very low pressures, You can get a gas at almost any temperature if you are at a low enough pressure. Look what else we have here. We have different state changes. When we go from a solid to a liquid, that's called melting, and you're familiar with that with ice cubes. And going from a liquid to solid is called freezing. When you go from liquid to gas, we call that vaporization. Vaporization can happen in two ways. It can happen by boiling, and it can happen by evaporation. Those two processes together are called vaporization, just making a vapor from a liquid. The opposite of vaporization is called condensation. Now, some students are less familiar with this. At first, they think they're less familiar with this, but everyone has experienced that kind of glass of ice cold water on a summer's day. You've got your ice cubes in there, and then you get the little droplets on the outside of the glass. That is condensation, where liquid water in the air touches this cold surface of the glass and then condenses into those tiny droplets that you see. The third set of phase changes is less familiar to some students. Sublimation is going from a solid directly to a gas. The most familiar example of this is dry ice. Sublimating, going from a solid dry ice directly to gas. Water can also sublimate. If you have a frozen puddle of water on a winter's day, that water puddle or that ice puddle will get smaller eventually over time as the water sublimates. Just happens a little less frequently and a little less obviously, so people are less familiar with sublimation. Deposition is the opposite of sublimation. So factories that make dry ice, they take carbon dioxide gas and pressurize and drop the temperature to create solid carbon dioxide, solid dry ice. There are a few other things to notice about a phase diagram like this. We have a critical point up here. The critical point is a point at which, if you get any higher in temperature, you can't have a liquid or a solid anymore. The only thing you can have is a gas. So at the critical point, once you're above the critical point in a temperature, then you can only have a gas. The other important point on a phase diagram is called the triple point. The triple point is where you can have a solid and a liquid and a gas all coexisting at the same time in equilibrium. So you can have ice in a glass of water on a hot day, but it's not in equilibrium. Eventually that ice will melt in the liquid, and so long as the temperature is above freezing. If you are exactly at freezing, 0 degrees Celsius at standard pressure, then that ice and that water can coexist together indefinitely. You can have ice and water coexisting at the same time so long as you're exactly on this melting freezing line. Okay. But at the triple point, you have all three. You can have solid and liquid and gas coexisting together in equilibrium at that specific temperature and that specific pressure. So let's look at those parts again. I just talked you through the graph, but let's get those definitions written down. So a phase diagram represents the different phases, solid, liquid, gas, as a function of temperature and pressure. The critical temperature is a temperature above which the vapor cannot be condensed. It cannot be changed to a liquid. It has to be a gas. The critical pressure is the pressure required to condense vapor at the critical temperature. So if you're at the critical temperature, how much pressure do you need to create liquid? The critical point is the critical temperature and the critical pressure listed together. In the phase diagram, we also have that triple point that I mentioned. It's the temperature and pressure conditions at which the solid, the liquid, and the vapor of a substance can all coexist together at equilibrium. So let's look at how we use a phase diagram to kind of collect information about a substance. So this substance here, we're looking at, we want to know what is the phase, solid, liquid, or gas, of a substance at 2 atmospheres of pressure and 100 degrees Celsius. So 100 degrees Celsius is here, this vertical dotted line, and 2 atmospheres of pressure is over here. So we're looking at a point right here. Is that solid, liquid, or gas? Well, we expect to see solids at cold temperatures, liquids at the medium temperatures, and gases at the highest temperatures. So we know that this must be a solid. What is the phase of a substance at 0.75 atmospheres and 100 degrees Celsius? So 0.75, we're right here. We're near the triple point, but we're not at the triple point. We're in this liquid zone. So here we expect the phase of this substance to be a liquid. This is the same phase diagram. I just squished it a bit to fit in these questions. If this substance were at 2 atmospheres, at what temperature would it melt? Okay, there are a few steps to this process. First of all, we need to remember that we have solid here, liquid here, gas here. Second of all, we need to remember that melting is going from a liquid to a solid. So we're looking at crossing this line right here. Thirdly, we have to find 2 atmospheres of pressure. So we're up here at pressure. Here's my 2 value. So right here is where I'm crossing the line. I want to cross the line going in this direction at 2 atmospheres of pressure. So I need to drop this line down, and it looks like that would happen at about, we're halfway between maybe this 150 and the 200. So I'm going to say at about 175 degrees Celsius. If the pressure of a sample of this substance at 0 degrees, so we're looking here, was decreased from 1.25 atmospheres to 0.25 atmospheres, what phase change or changes would occur? So we start at 1.25, we start up here, and we drop to 0.25. So we're going this direction, down, across this arrow. We're going from solid to gas. When you go from solid to gas, that is called sublimation. So that is the phase change that happens at that temperature and pressure. Same phase diagram here. If the temperature of a sample of this substance at 0.5 atmospheres pressure is decreased from 0 degrees Celsius to negative 50 degrees Celsius, what phase change would occur? So we're at 0.5 atm, we're here. And we're dropping from 0 degrees, which is here, to negative 50 degrees, which is here. And we're going in this direction. Remember, solid, liquid, gas. If we go from a gas to a solid, that phase change is called deposition. So that's how you read a phase diagram and how you can use a phase diagram to gather some useful information about a particular substance. Another kind of diagram you can see that has to do with heating or cooling a substance is called a heating curve. And a heating curve shows how temperature affects the phase of a substance. So how the phase of a substance changes as heat is added to the material. So you can see we have heat added on the x-axis and the temperature on the y-axis. And you can see that when you add heat, sometimes the temperature goes up, like here, but sometimes the temperature stays constant, like here. I hope that seems a little weird to you. If you're adding heat to something, don't you expect the temperature to go up? That's certainly usually the case, but according to this graph, it's not always the case. So if I have a pot of water on the stove, it might heat up for a period of time, and then the temperature actually remains constant for a period of time. The reason for that is because of phase changes. What we have down here at the, when we haven't added very much heat, this is where we have a solid substance. We start with a cold solid, and when we add heat to it, the solid gets warmer and warmer and warmer and warmer until we get to the melting point. At this level area of the heating curve, this is when melting occurs, at least if you're going in this direction. Okay, melting is happening when you continue to add heat. So that means you're going from a solid to a liquid. So you can have solid and liquid coexisting together at the same time here. Once you get all liquid, then the temperature starts rising again. So this is where you have a liquid. You keep on adding heat and the temperature keeps on rising until you get to the next part of the heating curve, and this is where vaporization occurs. This is where you have a mix of liquids and solids together. I'm sorry, I said solids. I meant to say gases, liquids and gases mixed together. And again, the temperature doesn't change as this process happens, as vaporization happens. The temperature doesn't start changing again until we actually get to the gas phase. Once all of the substance has vaporized into a gas, then the temperature of the gas starts increasing again. Here's a slightly tidier version of what we just drew. Notice that I only labeled before melting as you go to the right and vaporization as you go to right, but you can also draw the backwards version of the graph. And if you were going the other direction, you would have condensation as you go from gas to liquid, and you would have freezing as you go from liquid to solid. So why do we have this shape? Why does sometimes adding heat make temperature rise and other times heating doesn't make the temperature rise? So when you have those sloped lines with solid, liquid, gas, it's because you are actually heating and increasing the temperature of the solid or the liquid or the gas. On the plateaus, on those flat regions, phase changes are taking place. You're adding heat, but temperature does not increase. The reason for that is that there are intermolecular forces kind of holding the particles together in their solid form or in their liquid form. And the energy that you're adding to the system by heating it goes to break up, to disrupt those intermolecular forces. It's not something you need to worry about in CP Chem, but it is something you need to worry about in Honors Chem. I hope this helped.